Now, the next thing we want to do is that we try to go back, look at all we have learned so far in a unified point of view. Okay, here it's unified in terms of the integral, the calculus. Okay, so we say that if you try to understand physics well, you have to know calculus well. So you can see here, the idea is that without calculus, it seems that you have many different stuff in the classical mechanics. Like sometimes we talk kinematic equation, sometimes we talk about Newton's law and momentum and impulse, energy and work. Sometimes we have rocket problem. Sometimes we have drag force problem. Okay, but in terms of the calculus, you can see that it's just that if you have some, you start with Newton's second law. Okay, the central goal for the classical mechanics is to solve this equation of the motion. That's a mass equation to control any motion, Newton's second law. But to solve it, to find the velocity. Okay, we want to solve Newton's second law to find some kind of velocity. So you want to integrate Newton's second law. So then, depends on the situation, depends on the functional form of the force, because the force to control the motion. You can do different kind of integral, and then you introduce a lot of different stuff, right? So, basic idea is that Newton's second law, you have F equals to m dv over dt. You try to integrate this equation. But how can you integrate it? You can integrate with respect to time t, with respect to position x, or even with respect to velocity. So it depends on the functional form of the force. In fact, so you can see the most simple case is F equals to constant. Okay? In that case, the integral will directly lead to kinematic equations. If it's a constant function, constant acceleration, so you can write it as F dt, okay, F over m, which is, so, okay, F is constant, that means A equals to F over M is a constant, right? You can actually calculate it. And then, the equation becomes A equals to dV over dt, right? So, now see that once you introduce this, you can see this is actually definition of the expression. But here, the acceleration equals to, you need first calculate acceleration from F over M, right? And then integrate that, we know how to do that. If you integrate it first time, so you write it as A dt equals to dV, right? And you integrate it both sides. This side for time from 0 to final time t. This is from initial velocity to the final velocity. So that will lead to an important equation, V minus V naught equals to AT, right? Integral of this gives you AT. So this is one of the kinematic equation, and then you further integrate it, you get the position function. Delta x equals to x naught t plus 1/2, V naught t plus 1/2 AT squared, right? So that's a kinematic equation. This integral is very simple. This is the integral with respect to time, but it's very simple because the force is constant. But if force is not a constant, okay, if force is a function of time t only, you still do the same thing here, right? Okay. But in this case, force is not constant, so acceleration is not constant. So when you do this kind of integral with respect to time, it could be some more complicated function of dependence. dependence here. Right? So a typical then we give those integrals some name. Okay, momentum and impulse. Remember how can we do that? We have F over M multiplied by dV over dt. So if we multiply both sides by dt, we get F dt equals to M dV. And integral of left hand side, and we integrate it. So F dt, okay, from the initial time to the final time. And the right hand side is M integral of M dV from the initial velocity of the final velocity. So this integral, because this quantity will give you the impulse. And right hand side you can check, it will give you mv minus mv initial. So that's I equals to delta P. Momentum, impulse, the impulse momentum 0, right? And now, if f is a function of the position, how can we integrate that equation? Here, we multiply both sides by dt. Okay? And this one, we have to multiply both sides by dx. So we get f dx equals to m dv over dt multiplied by dx. Right? And since dx over dt is v, so it becomes f dx equals to mv dv. And then you integrate both sides, okay? This is from initial position to final position. This is from initial velocity to the final velocity. So left hand side, we call it work. That's the definition of the work. So W equals to this at 1/2 mv squared minus 1/2 mv naught squared. We call this work net energy 0. W net equals to delta K. Right? So that's some general stuff. And we can, for some other situation, the force can depend on some other quantities. For example, if force depends on F velocity, if it's a function of the velocity, then drag force is that kind of force, right? It depends on the velocity. In this case, you get, you just directly write it as F dt still equals to m dv. But in this case, if you want to do the integral, so you have to move f to this side because it's a function of v. We have to move all the v dependence to one side. So you want to write it as dt over dt equals to f m over f dv. Okay, and then you integrate both sides from the initial time to the final time. This side from initial velocity to the final velocity, u naught to v m over f v. This is a function of v dv. So this is a typical drag force problem. Okay, you can go back and check how we do that. But here the idea is to integrate it with this. And then we have our rocket problem. All of them, we assume the mass is a constant. Okay? So all of them, you have constant m. So for varying mass, if it's varying m, then you have to write down the Newton's second law in a more general form. F equals to m dv over dt plus v dm over dt. Okay. And then you can see once you have varying mass, of course, the calculation will be much complicated because because you have two terms here. So the integral is not very straightforward. Like even for this very ideal consideration of the blockage, it's very ideal model, we still do this naming stuff. So, I hope I kind of gave you some feeling about the classical mechanics so far. So what we're actually doing is simply solving Newton's second law. All we have to do is try to solve the Newton's second law, okay, in different situations. So that's it. And for any kind of mechanics, there are some similarities. You always have some master equation to control the motion. And your target is to solve that master controlling equation. For example, in quantum mechanics, all you have to do is to solve Schrödinger equation. Okay? In E&M, all you have to do is to solve Maxwell equations. So, in other words, we think that physicists always deal with all kinds of differential equations like that. Okay? That's it.